Hello guys, and welcome back to my YouTube channel. It's me, Afraz the Knowledge Man, back with another video. In today's video, we're going to be diving into numbers. Numbers, numbers, numbers. They're everywhere. Take a look around. The letters in your name, your age, the devices you own, the price of the device that you're watching this video on, the length of the video, or maybe the seconds it's going to take me to complete this intro. The balance of your bank account maybe, or your rent, the count of rooms in your house, the score of a soccer match, etc., etc. The list just keeps going on and on and on. And it's so long I could just sit here all day or even all year long just talking about examples of where we see numbers in real life. But the main question we all wonder is, what are numbers? What are they? And since, well, forever, humans have been trying to identify numbers. And finally, after years of thinking minds doing their things and thinking, and years of mental development, we've finally done it, folks. We've classified numbers into a number of different sets. See what I did there? Now, numbers come in a variety of different numbers. Let's start off our list with natural numbers, which may sound more familiar. Natural or counting numbers. Natural or counting numbers are the first numbers that we all knew as toddlers when we began learning. And they start at 1 and they keep going all the way up to infinity. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to infinity. We began learning as toddlers. They begin at 1 and go up all the way to infinity. And we can write them in set form as n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way on and on to infinity. And as you may have guessed, the set of natural numbers is denoted by the capital letter N. Then we have whole numbers. Whole numbers are the second type of numbers. And true to their name, whole numbers are whole and not fractional numbers. Whole numbers are whole and not fractional numbers. The set of whole numbers starts at 0 and goes all the way up to infinity. Just like natural numbers. But do you guys see a coincidence here, or is it just me? I can see, and I'm pretty sure you do too, that if we just add a 0 to the beginning of the set of natural numbers, we get the set of whole numbers. And so we can say that and so we can say that the set of natural numbers is a subset of the set of whole numbers. But why do whole numbers have the addition of 0? So, well, let's say there's a match, for example, a match where no goals are scored, a soccer match where no goals are scored by either team. So we can represent this, or if someone's trying to tell someone else that there were no goals scored in today's soccer match, they can say the score was tied. The score was tied at 0-0 as both teams scored 0 goals. Something like that. That's a pretty good example, I guess, for the use of 0. And we can write the set of whole numbers as W equals 0, 1, 2, 3, 4, 5, 6, 7, and it keeps going on till infinity. And the set of whole numbers is denoted by a capital W. Next up, we have integers. Integers. Now, what are integers? Up till now, what we've talked about, we've always had positive numbers and like just the behavior we've been talking about. Sometimes we can come across opposite behavior. And for this behavior we use positive and negative signs. We use positive and negative signs. And let's say, for example, you're standing on a number line. Conventionally, on the number line, taking any steps to the right is considered positive, and taking any steps to the left is considered negative. Which is also conventional, that it's considered negative. The set of integers contains all numbers from negative infinity to 0 to positive infinity. And a worthwhile note to be taken is that they can't be written in decimal or fraction form. And the set of integers is denoted by capital Z and is as follows. Z equals we can just say these dots, ellipses, mean to say that we're coming from negative infinity. Then we have -3, -2, -1, 0, 1, 2, 3, and then it keeps going all the way to infinity. And that's the set of integers. Oops, I just realized. There we go. There we go. And yeah. Next, we have rational numbers. What are rational numbers? Rational numbers. Let's start off with the definition of rational. The word rational is derived from the word ratio. And true to that, rational numbers are the ratios of two integers. Let me just write that down for you guys. The word rational means ratio. And true to their name, just like whole numbers, these numbers are really true to their name, aren't they? And true to their name, they are the ratio of two integers. And there we go. For example, we have -3, 4/5, 7/9, 37/100, 8.97, 9.78, 7.89, etc., etc. And yeah, as we can see over here, even 3 is an example of a rational number. And yes, it is, because 3 can be written as the ratio, -3 can be written as the ratio of -3 to 1. And in general, we can say that rational numbers can be written as P over Q, the ratio of P and Q, where P and Q are integers and Q isn't 0, because if Q is 0, then the fraction is going to become undefined. And when Q is 1, the fraction is simply an integer, such as -3. So we can say that integers are a subset of the set of integers is a subset of the set of rational numbers. Let me just write that down for you guys. In general, rational numbers can be written as P over Q, where P and Q are integers and Q is not equal to 0. Never mind. And Q is not 0. Not 0. Because if Q is 0, the fraction becomes undefined. Let's use this. Yep. And these aren't the only numbers which are included in rational numbers. Also, fractions which result in limiting decimals or recurring decimals are rational. And the perfect squares, the roots of perfect squares, are also rational. The set of rational numbers is denoted by the capital letter Q, which means quotient. And so the roots of square, the square roots of perfect squares are also counted as rational, and the set of rational numbers is denoted by capital Q. Yeah, that's about it, and we can put some examples of some perfect square roots. Okay, so we can have, say, 361, or 49, or 100, or 81, 289, I'm pretty sure 23 squared is 526. Correct me in the comments if I'm wrong, please. And 441, etc., etc. There you go. And yeah, that's it. Yeah, and that's all about rational numbers. Now let's talk about irrational numbers. Irrational numbers. Irrational numbers, just as the name would suggest, are quite the opposite of rational numbers. Let me correct myself, they're totally the opposite. Irrational numbers are the fractions with non-terminating or non-recurring decimal forms. The most common examples that I'm pretty sure we've all heard of are pi or e, and the golden ratio. By the way, e is Euler's number. And also included are the square roots of imperfect squares, because they have non-terminating and non-recurring decimals, or non-recurring decimals. So let me just write that down for anyone trying to take notes. That looks better, I guessed it. Yeah. And examples, other examples, of course, because these are just the most common or famous, popular. Other examples would be under root of 2, under root of 8, what did I do? 800, or 3,111, or just 31, 50, 68, oops, 678, etc., etc. etc., etc. And yeah, that's all for irrational numbers. Now let's talk about real numbers, which are the real deal. Real numbers. Real numbers, as the name suggests, are real. And the set of real numbers is you could consider it as the universal set of the set of rational and irrational numbers, because it includes all numbers that can be written in decimal form, and all other numbers as well that we've talked about up until now in the video. And it's denoted by R. So let me just write that down. The set of real numbers is, or can be considered the set of the universal set of rational and irrational numbers, as it includes all numbers that can be written in decimal form. It is denoted by capital R, and yeah, that's it. And yeah, that's all about real numbers. And now let's talk about imaginary numbers. I'm pretty sure you guys saw it coming, didn't you? Because, well, there wouldn't really be a need to name a set named real numbers, or like a category named real numbers. So, yeah, it's because imaginary numbers exist. So, here we have imaginary numbers. Imaginary numbers. As the name implies, imaginary numbers aren't real. Just imagine the time when thinking minds were trying to think and they were working on their calculations, but they got stuck because they couldn't simplify some certain result and express it in the form of some normal numbers that they used at that time. Because, well, it simply didn't exist at that time, so of course they weren't going to be able to represent it in such a way. Although realized by the Greek mathematicians, René Descartes coined this derogatory term for numbers which had the under root of -1 as one of their factors to regard them as fictitious or useless in the 17th century. Later on, the works of Leonhard Euler and Carl Friedrich Gauss made imaginary numbers more sensible. Consider numbers like the under root of -2 and the under root of -5. Their squares give us a negative result. For example, when we square these numbers, the results are -2 and -5. And those are real numbers. Let me just write that part down. Voila. I didn't skip. Yeah, there you go. Yep, that's imaginary numbers. And thanks to the works of these thinking minds, imaginary numbers aren't considered useless anymore. They're actually used in complex calculus computations and the calculations of current and voltage in electric circuits, which, as we know, electricity plays a huge role in our lives. because electricity is related to the network, and the network is related to gamers. Let's recap. The numbers which have under root of -1 as one of their factors are called imaginary numbers. For example, under root of -1, under root -2, under root -3, under root -4 are all examples of imaginary numbers. And under root of -1 is denoted by iota, which is a cursive I, and call it iota, because the thinking minds want it to be named that way. And we can write the numbers that I just mentioned, under root of -1, -2, we can write them as iota, 2 iota, 3 iota, 4 iota, etc., etc. And yeah, that's pretty much all about them. Let me just write that down. Here we go. There we go. Next up, and lastly, we have complex numbers. Complex numbers. As you can tell from the name, they're quite complex. Well, that's what you'd think. The name is quite scary for me too. They're not too complex. Complex numbers are simply an imaginary number combined with a real number. So that would look like, say, we have a real number, say 63, and then we have an imaginary number, say -7 iota. So 63 minus 7 iota is simply a complex number. Not too complex, is it? Yeah, I thought so. They're represented in standard form. They're written as a plus b iota. Their standard form is a plus b iota, where a is the real part and b iota is considered the imaginary part. And yeah, real numbers lie on a number line, and complex numbers lie on a 2D flat plane. Not a ripoff at all. And just like imaginary numbers, complex numbers aren't useless. They're used in lots of applications, like the signals and systems and Fourier transform. Yeah, that's pretty much all there is for today. Let me just write what I just said down, because this isn't the proper way to write it, is it? Here you guys go. It's more informative. And yeah, that's about it for today, guys. I'm going to have to end the video here. See you guys in the next video. I know the video didn't end. Cut that part out, please.